The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
The basic concepts of reachability, talking about how we can represent reach sets in continuous spaces. Then Giovanna is going to take it over and talk about some applications in robust motion planning. And then Gerardo is going to talk about how we compute reach sets and focus on these two, on closed loops and funnels. Okay. So reachability is a task of figuring out what states a dynamical system can possibly reach or be at a certain time. So for example, if we have these two systems, we have a finite state machine, a discrete system, and a continuous system, and these are the starting states. Then, and these are our actions. We can move east or north here, and we can move east or north with these velocities over there. So after 1 second or one time step, we can be in either of these two states, or we can be anywhere in this area. And after 2 seconds, after 3 seconds, and so on. Okay? So this is what reachability does. And the motivation for this, one of the applications for reachability is for verification. Verification is just the task of making sure that we are never going to reach any bad states. So for instance, let's say we have a microwave. A bad state is the microwave being open and on. We want to make sure that these bad states are never reachable. So what we do is we compute the reachable sets, and we check for intersection with the bad states to see if the microwave is on and open, or like over here. Let's say we have these obstacles. Let's say we have a wall or some other obstacle over there. We want to, this is bad, right? Because we can reach this state and it's the same as a wall. Okay? Any questions so far? Feel free to interrupt me anytime. Another motivation for reachability is for robust motion planning, that I'm going to talk more about. And I have a video of this. So what we can do with reachability is stuff like this. Okay. So this is done using flow tools, which use reach sets, reachability. Gerardo is going to talk more about this example. Okay. So now, before we talk more about these cool examples, let's just formalize concepts. Let's define some things. So let's go back to the same system that we had earlier. This state machine. We have a finite set of states x, a finite set of inputs u, which in this case are east and north, and a transition function, and let's say this is just deterministic to keep things simple. And we have a set of initial states, x0, which I label as red. So the reach set is defined as the set of states that we can possibly be in at time t. So more formally, there exists a sequence of t control inputs that will take us from this initial state to the corresponding reach state. So let's say, for example, we have that state. It's in the reach set at time 3 because there exists a sequence of 3 inputs. In this case, this is one such sequence. There's 2 more that will take us from the initial state to there. Okay. And then the reachable set, reachable set, is defined as the union of all reach sets for time less than or equal to t. So the reachable set at time 0 is just the initial set of states, and time 1 we have the union, and so on. Okay. So the reachable set is what we use to test for intersection with bad states, because that's all the states that we can possibly reach at some from time 0 to time, sometime. Okay. Now, as some of you may have figured out by now, there's a simple way for finite state machines that we can compute reach sets. So for example, let's say we wanted the reach set at time 2. One way, the easiest way we can do this is to break this up into time steps, into single time steps. So instead of computing it straight for time 2, let's first compute it for time 1. And now we can use these two states as the set of initial states and compute the reach set for one more time step. And that gives us this reach set. Okay, any questions? Okay, and the reason why this works is because reach sets are semigroups, and semigroups satisfy this equality. So we can not just break it up into single time steps, we can break it up into any 2 times, S and T. Okay, so all of this was for finite state machines, but for continuous systems, things get a little more complicated. It's a lot of the same concepts, but we need to handle a very important issue, and that is how to represent reach sets, or just sets, regions in space for continuous systems. Because in a finite state machine, we could just enumerate the list of states in the reach set or reachable set. In a continuous system, we need some other way. We can't just say it's every point for which there exists a sequence of control inputs, because that can be infinitely many points. So what we do, we have 2 types of representations that we like. One is convex polytopes. That's just the generalization of a convex polygon into n space, into n dimensions. And we have 2 basic ways that we can represent these convex polytopes. One is with a list of vertices, like this, A, B to F. Okay. And then the convex polytope is defined as the convex hull. And in case someone doesn't remember what a convex hull is, let's say we have just a list of points. The convex hull, imagine you have a rubber band, and you're going to stretch it up and then let it go. And what that's going to do is this. And the convex hull is just the whole area inside the rubber band. Okay. And then another way we can represent convex polytope is with a set of inequalities. So for example, here we have 4 lines. Here's the equation for each line. So let's say this red line, we want anything below the red line. This blue line, we want anything to the right, so anything greater than, and so on. So this area is just the intersection of all these inequalities. Okay, and each of these representations has an advantage over the other. Vertices are good to test for emptiness, because if with our set of vertices is empty, then our convex polytope is going to be empty. These inequalities is very useful for testing membership, because for any point we can just plug it into every inequality, and if it's true for every inequality, then it is in the polytope. Okay, and convexity, I'll just explain it briefly. Convexity means that any 2 points inside our region, is going to be convex if for the line connecting these 2 points, all the points in that line are going to be in the region. So here you can see that this is convex, and here this red area is outside the region, so this other region is non-convex. And convexity is going to be important for the algorithms later on. Gerardo will talk more about them. Okay, other than convex polytopes, we can also use ellipsoids to represent reach sets. So ellipsoids are just the extension of ellipses to n spaces, n dimensions. And a convex polytope is defined by this. X is just all the points inside the polytopes, inside the ellipse. V is the center, and A just tells us about this, how deformed the ellipses. Okay. Any questions? Okay. And one of the reasons why we like convex polytopes, why we like ellipsoids, is because of their closure under linear operators. So let's say we have P that is a convex polytope or an ellipsoid. Then if we have a matrix A, then A times P, which is defined that way, is still going to be a convex polytope or an ellipsoid. So if we have something like this, then this can maybe get deformed, but it's still going to be a convex polytope. And the reason why this is nice is that if we have a linear system like defined this way or this way, then if we start with if we start with a convex set of states, then our reach sets are always going to be convex because we're just multiplying by A. And this is very nice to represent. This tells us that our representation is going to be good because we can just use convex polytopes, ellipsoids, and stick with those. Just take a step. Okay, and so even though the reach sets will be convex, the reachable set might not be convex, but it will always be a union of convex polytopes or ellipsoids. For example, let's say in the previous example, we started here. Then after one time step, we were here. So these are two things, and then our reachable set is the union of both of them. And this is clearly not convex, but it is a union of convex polytopes. So we can represent everything with the union. Okay. Any questions before I move on to Savannah? Okay. Thank you.
Okay, so now that you have understood what reachability is and like how to represent reason sets, and before we dwell into more theoretical aspects like how to compute reason sets, let's look at some cool applications of reachability. So there are many applications of reachability to robots and like complex systems, biological systems. One of the applications has been talked about before, is like robust motion planning. So here the idea is to like move a glider or an airplane through lots of obstacles, even in the presence of uncertainties and disturbances. You don't want to crash into any of the obstacles even when there are like disturbances. There's also applications of reachability to control complex systems like bipedal walking robots. Here you can see that you're controlling a robot to take a sort of water or something. And more importantly, reachability is like used for verifying safety properties for like safety critical systems like air craft collision avoidance. So in this lecture, we'll go into more detail on one of the applications, that is robust motion planning. If you're interested in other things, there are papers and the references that you can look into it. So the goal of motion planning is to find a set of control inputs that take you from like a start state to the goal state. So in this example, without colliding with any of the obstacles. So here, this is like one possible path from the start state to the goal state. So this looks nice, like it doesn't collide with any of the obstacles. But if you get the controls for this path and then give it to a real robot, you might find it doing something like this. So this is because the path that algorithm that we use for planning this path does not take into account any of the uncertainties in the environment or uncertainties in the model. So there are different kinds of uncertainties. One of them is environmental disturbances, like there is wind here, so that can move your robot off your planned path. And there can be modeling errors. The model that you use to represent your complex system might just be an approximate, so the real world is different. And there is state uncertainty, the things that you use for measuring your position or velocity are also like approximate, so there are uncertainties. Moreover, there can be some randomness in the initial conditions. Like you're thinking of starting a robot at like 0, 0, but in practice you might actually be starting at like 0 plus epsilon. So there is randomness in the initial conditions. So the goal of robust motion planning is to have some guarantees with some confidence that the system will reach the goal state without hitting any of the obstacles, even in the presence of these uncertainties. So this is the problem. So let's look at some of the solutions that have come up for solving robust motion planning. So this is a timeline. So there are 3 different systems that all of them have a core concept where they kind of use some representation to represent the reach sets, a set of possible states that the system can be. And then instead of searching for a single trajectory through the state, they search for these representations. So that like if you find a set of representations that can go from the start state to the goal state, you don't hit any of the obstacles. So earlier, Bradley and Zhao and Fraser came up with this concept called flow tubes. It's a way of representing reach sets, and you will learn more about this later from Gerardo. So what a flow tube basically is that you have a set of initial state and you have a set of goal state. So flow tube is like a combination of all the possible paths that can take you from any point in initial state to any point in goal state. So this is kind of representing all possible places you can go. So then like you search for this flow tubes to be a path to get your motion plan. And in 2006, like Hoffman and Williams combined this flow tubes with temporal constraints so that you can also reason about complex systems that require spatial and temporal coordinations, like the walking robot that you've seen before. And there was also work by Ross Tredwick's group about using funnels for motion planning. So funnels is also a similar concept to flow tubes. It's kind of like a stability region around your path, so that if you're inside the funnel, you're guaranteed to be inside the funnel. So in this lecture, we'll go into more details about motion planning using funnels. And again, there are references for the other papers when we can look into them. So what's the idea of using funnels? It's like for every path, you complete some region around that path. That's like a stable region. That's called funnels. You'll learn more about how to complete funnels later, but for this part of the lecture, we'll assume that we know how to complete funnels. And like we'll see how to use these funnels to do motion planning. So the previous example you see that this is the funnel for a blind path. You can see that it collides with a tree, so it's not a stable path. The other thing is like these funnels are computed for some uncertainty model that you have. You need not know everything about the uncertainties that are present, but like some bounded model that, and then you compare a funnel for them. Any questions so far?
Please say again the definition of funnel.
So it's kind of some invariants around invariant path around like you have a path of like it's like some invariant region around that. So I think Gerardo will explain more about it. So the thing that you have to remember about funnels is like if you're inside the funnel at a point, when you exit, like when you come out of it at some time, then you'll still be inside the funnel. So it's like, do you want to explain more?
Alright, so a funnel is basically, it's kind of like a reach set around a certain point. So usually the way that you do it is you have some nominal trajectory, and then at each node point in that trajectory you compute some kind of reachable set at that node point. And so you blow it up and it becomes some kind of ellipsoid. And as long as you're within that ellipsoid, no matter what disturbance you get, you're going to go back towards the nominal path. And then so when you join all of those ellipsoids over the trajectory, then you get a certain kind of funnel. And as long as you're inside that funnel, you're going to stay on that funnel and you're going to be on the path that you want to be at with some disturbances, but you're going to stay. So that the gray thing right there would be an example of a funnel. As long as you're in the funnel, you're going to stay in the funnel, basically.
So is this considered the control, or is it only the dynamics?
It's the dynamics with the control, so it's the closed loop system. Yeah.
Yeah, so you'll learn more about those like during this.
Okay, let me just quickly add. So a funnel is a type of flow tube, right? I mean, just different people either use the same terminology, use different terminology. Right? Each of the applications of flow tubes has some invariant, which is different. Right? And the particular invariant on this one, right, is that if you are in the funnel and you apply an LQR controller, right? Instead you're done, then you're guaranteed to stay within that tube.
But I thought the flow tube is actually like getting smaller and smaller in the bottom. So this one's like a large at the bottom.
Not necessarily. In general, flow tube is simply a bundle of trajectories which capture some common feature. And then maybe that they move to a limit cycle, or maybe that they stabilize to a point, or maybe that they move to a goal, and maybe that they always maintain their state within the tube. In a funnel, they focus particularly on stability to disturbance and staying within the tube.
So let's look at another example which is kind of useful to combine reachability with motion planning. So here is another situation you are trying to go from the start state to the goal state, and then you have a set of trees lined up. So there is a path that goes in between the trees. This path looks kind of risky because it's very close to the two trees. But there is another path that you can take it around all the trees. So intuitively, the first one seems risky and the second one seems like safe, but maybe that's not true. So that's why we need to combine reachability with motion planning. So if you combine that, you might find that the first path, if you compare the flow tube for the first path, it does not hit any of the trees and it's indeed safe. And it might happen that for the second path, it's like more susceptible to the disturbances and you can actually indeed go and crash the tree. So that's why we need reachability analysis and what you combine with motion planning, because what's intuitive is not actual. Okay, so far it's all about offline planning. So we assume that we know everything about the environment, like where the obstacles are, but that's not always true in the real world. So you do not know all the obstacles beforehand, and you get to know them as you move through the space. So one problem about doing online planning is that you cannot do any expensive computations during runtime. And all of these funnel calculations are like very expensive. It requires like solving an optimization problem and takes like a couple of hours to finish them. So you cannot compute funnels on the fly. So the idea here is to like compute the funnels offline, compute like all possible funnels from the start state to the end state, and then use this library to as you move through the space. Like so you have the same state that going to the start state and the goal state on that end. So like these are like set of possible paths from the start state to the end state, and then for each possible trajectory you compute the funnel. And the idea of online planning is to now find a sequence of these funnels that you can compose that takes you from the start state to the end state without dealing with the obstacles. So an important component here is finding a sequential composition of funnels. Any questions about this?
So why plan? You're doing a forward search with funnels. Why use funnels instead of something like RRT?
I actually don't know what RRTs are. So.
Can I guess at the answer?
Well, I'm trying to let them.
Why use funnels instead of RRTs?
Well, or why use funnels? Or,
well,
as opposed to anything else?
I guess RRTs, you have like the classical example where you want to go through a very, well, if you want to go through a very narrow region, well, first of all, I guess RRTs are going to have a hard time finding that narrow region because you need like a point to go through that. And then RRTs by themselves don't really account for errors, maybe some extension. But funnels, you can be sure that you're always going to stay inside the funnel. So this is for robustness, just to make sure that we don't crash. Does that answer the question?
Do you want to answer it?
Yeah, I think what he just said, it's the point of the funnels is that they provide a control policy. The actual reference trajectory that you have on the left is the motion planning. But with the funnels, you get a control policy because when you start executing the motion plan, there's always going to be a disturbance. So you want a control policy that keeps you on that trajectory. And there's all sorts of control policies. You could use simple PID controllers. They work in some cases, but funnels provide better guarantees for complex dynamic systems.
So the idea is also if you have trajectories and then computing funnels around that, and then if you're using these funnels components, you compose them to find your path to the space that you want to go. So there's so you cannot always compose funnels. Like there are some propositions that are like legal and some of those are not legal. So consider this example, like take time going from left to right. So you have a situation where there's a funnel, like you're trying to compose like a bigger funnel with a smaller funnel. And you have another situation where you're trying to compose a smaller funnel with a bigger funnel. So what a funnel is like, it's like a region of stability. So like which of these combinations do you think is like a legal composition? Or which of these is illegal? Or illegal or illegal, I mean that like which of these guarantees do you have the safety properties that you want?
Bottom one is actually work. The top one, if you're at like the very top edge of the bubble, you're something with now and then the second one.
Yeah, that's true. So the first one is like illegal, and the second one is a legal composition. So why is that? So if you're inside the funnel, what this guarantees that you will stay inside the funnel, but it could happen that you can go through the funnel and then you're outside the second funnel. And after this step, you can go anywhere. So you can crash. But if you're inside the second phase, after you move through the first funnel, you're still inside the second funnel and you will guarantee to satisfy safety properties. So now let's actually look at this online planning algorithm. So this is your space that you're trying to go through. I just replace the keys with like conics polytopes. It makes the analysis easier. So this is the algorithm. Let's go through each of the steps one by one. So since this is online planning, you do not have all the information beforehand. Like initially you don't know anything about the environment and you get to know more about it as you go. But you still have like an initial planned funnel sequence that takes you from the start state to goal state. And like then you check for any new obstacles information that you got from your sensor. So this was the region that you can see, and you can see some obstacles. And you also get the current state of your robot. This is also subject to uncertainty as I told before, so it will not be exactly 0%. And you check if your current funnel path collides with any of the obstacles you have seen so far. And in this case, the answer is no. So then you apply the control corresponding to this funnel for this particular location and time. And that takes your robot some steps forward. Then you go through and then do this step again and again. So you again update obstacle information. If there are more obstacles here, you get the current state of the robot. And then you check if the current plan collides with any of the obstacles. And in this case, yes. So since it collides with the obstacles, you need to now replan funnels. So how do you replan this? You have all this library of funnels, so you go through each of them, and then like you find one set of funnels that has you find a set of funnels that starts with your current location and does not collide any of the obstacles. So this is like one possible new funnel sequence. And then again you apply controls corresponding to that new sequence. And do the loops. I'm doing this 2 or 3 times more. Get the position, check if it collides, and again it collides. So you replan it, get a new path, and like apply the control for that funnel, and then get more information. Again it collides, so you have to replan the path. Okay, so now you reach the goal. So this is how like online plan using funnel libraries. Any questions about it?
Can you say more about the computation of the funnel library? So they generate a set of funnels which cover the complete state space? Yeah,
so it's like there's every possible initial point, every possible start endpoint, and so then you can like you do not always have it for every initial state in between because like, you can compose all these other funnels. So like if you're doing from every initial state to every, so you do not have a funnel that exactly starts at your initial position. Like if there is a funnel that's already started somewhere, where it goes through your funnel, goes through your initial point, you can use that. So it's a truncation of the funnel. That's what answers your question. Any other questions?
What guarantees, like, if it really is an online problem, that you're not going to run out of a funnel, like that you won't reach a dead end? Will it be adaptable enough to make a U-turn at all times, even if there's some like latency, it doesn't like perfectly time it? Are there robustness that you'll always be able to find a path, even if we have guarantees that you'll always stay within a funnel?
So are you asking about the situation where like you got in the deadline and you have to backtrack?
Yeah, just because these obstacles come out of nowhere seemingly, that we don't have a guarantee that the funnel is safe through the entire duration of our execution.
Yeah, so that's an important point. Like, I don't know if this algorithm currently does it. I think it can be easily adapted to backtracking and certain other thing, come back and do it.
Even for robots that can't actually backtrack?
If the robots cannot come back, or?
I mean, I guess it's just like a UAV, it couldn't do that. I was saying, like, what guarantees do you need to have about, like, the obstacles, because it's an online setup, right?
Maybe you have, like, some initial information about some kind of obstacles, like, you can find a path to a trajectory. Like, you can find a trajectory that goes from the start state to end state. It's like, it's not like there's a wall here that you cannot go.
Well, I'm just gonna say, like, if you're in some kind of glider that can't necessarily, like a quadro can stop, go backwards, stuff like that, then you'll have funnels that can plan backwards. But if you're in some kind of glider and you're going straight at a wall, like, there's no guarantee. You're done. Like, I mean, even humans, they make errors. There's like situations that humans can't dynamically get out of. So if your system is dynamically not going to be able to make a sharp enough turn or go straight into something, no matter how smart your planning algorithm is, no matter if you're like, there's a wall right there, stop, you can't stop, you're just going to go straight at it. There's obviously situations, pretty much like any planning algorithm, that you're just going to crash. Hopefully, you're in a situation where you're not flying a wall. If it's also based on how far away your sensor can see. If your sensor can only see 5 meters ahead, and you're going 5 meters per second, and you plan in 1 second, you're going to have to make perfect decisions. But if your sensor has perfect information about the environment, then what seems like the initial best path may not actually be once you know the full environment. So it depends on dynamics and sensors.
Any other questions? Okay, so finally I have some demos showing simulations of helicopter moving through those obstacles. Let's see how we can go through really quickly these spaces. So this is the end of application. So we have seen how to use funnels to do robust motion planning. We have seen how to do offline planning and how to do online planning using a sequence of funnels and funnel libraries. Now we'll talk more about computing these funnels and flow tubes with other kind of presets.
Yeah, so I'm going to talk about how to actually compute them, how to compute flow tubes and funnels generally. I'm going to give an example of what each one is used for. So we had the question before, like, how are flow tubes and funnels different? Flow tubes are... So the easiest way is they're both some kind of way to guarantee that their robustness guarantees. So say you are here, you want to be here. They're both most planning algorithms, you get some kind of path from here to here. But say there's some disturbance that pushes you down here or something. You don't know if you're going to be able to reach there or not. What a flow tube is some kind of set of trajectories that'll basically go from some initial states, which are here, to some goal states over here. And basically, if you're within this flow tube and you get pushed down to a different trajectory, you know how to get from here to here anyway. So you don't really care if you're pushed as long as you're still within here. A funnel, let's see. So a funnel is, say you compute some nominal trajectory around here. Using the system theory and stability theory, you know that with your control inputs, you're going to stay at each of these points, and you're going to stay within here, within these circles. So if you get pushed down here, you know you're going to be able to get back onto your path, and you're going to try to converge back to your nominal path. So you have some sort of funnel. Yes.
I have a question. How complete is the funnel? It sort of relates to what Brian was saying. Is
completeness as in like these edges, or
well, if you have a high-dimensional state space, does the funnel cover it completely?
There's a set of funnels.
A set of funnels.
So the question wasn't about the individual funnel, right?
Okay.
But in the particular, in Pedder's right, when he generates a set of funnels, does the set of funnels completely cover the space?
It depends how much time you want to put into it, generally. If you only compute two funnels, one of them goes over here and one of them goes like here, then you're not going to be covering the state space. So it depends on how much computation you want to do offline previously. So you compute a set of funnels that's here, another one that's right here, another one that's here, and you have your big library of funnels that cover the whole space.
I think I skimmed that paper, and yeah, I think it is probabilistically complete.
Okay. Yeah. All right. Yeah, but I mean, as far as computing where you're going to go, if you compute that path, then you should be good. But yeah, you're right. The probability. Alright. So here's what I explained. Normally you have your optimal trajectory, but if you get pushed off it, you may not get back to the goal state. But if you have a set of trajectories that go from some initial states to your goal state, and you stay within that, you know how to get to your goal state even if you get pushed. Okay, so some ways to approximate flow tubes, you can use some kind of polytope, which is, as Gabriel explained previously, as long as it's a convex polytope, you can take that cross-sectional area and you can propagate it down your flow tube. You can also use ellipsoids or rectangles as cross-sections. An important point is to know that they're inner cross-section approximations. So as you see here, this would be your actual flow tube, but your approximation has to be an inner one because that guarantees that you're within the flow tube, but it means you may also miss some of the outer trajectories, which also is, if you want to compute a better approximation, you're going to get a better flow tube representation. Okay, so robust planning, you plan a trajectory from here to here, and that should be good. But then you get disturbed, you're still within the trajectory, so you're still good. But some work done by Professor Williams and Hoffman shows that, so what do you do when you're actually outside of the funnel? Now what you can do is temporal planning. So using the algorithm that we previously learned in class, you can take your goal state and move the timeline back to a different time. So here, this flow tube is, if you're here in a certain amount of time, can you get to here? And if you get outside of it, then you can't do that anymore. But you can just use our algorithm and move back the goal time. And then when you move the goal time, the whole funnel shifts because now you can be over here, and you don't care about getting here at this time. You can get here at this time now. So then you move over, and now where you were, you can get back into it because you're now inside the flow tube again. So that's okay. So one example is humanoid footstep planning. So this takes a complex system. You have a bunch of different parts of the system. You have like your center of mass dynamics, you have your leg dynamics, foot dynamics, and so what you're trying to do here is plan your footsteps forward and through time. So you have your original plan of where you want your footsteps to be for different parts. So there's discrete things that happen in the system as we previously seen in the lecture. So one thing that can happen is your left foot hits the ground, and then your right foot lifts off, your left foot lifts off, or your right foot hits the ground, and then your left foot lifts off. So those are different things that can happen. So you have certain temporal constraints on the system that you want to adhere by. And so as you start planning, you have flow tubes to get you from one step to another step. And that guarantees that you're going to stay within those. Even if you get disturbed and get pushed, your feet can still get from one step to the other. But then also with the thing that we saw in the previous slide, you can move the timeline back and forth as long as you're within your temporal constraints that you had. And then, so those are flow tubes for the feet, and that will guarantee that your feet go where they want to. But you can decompose the system to also have flow tubes for the center of mass. So what the center of mass does is it can be broken down into separate flow tubes. So does that make sense? So this was the humanoid footstep planning that we saw previously, and now you understand how the feet are planned to go to each of the blocks. Let's see if I can get a video.
I have a quick question. You said you have like a separate flow tube for the center of mass, but aren't they really just the same flow tube in a high dimensional?
Yeah, but that's when you decouple a system, then you can do individual flow tubes rather than a full system, like high dimensionality.
Is it hard to recouple them? Like, how do you know they're consistent once you do that?
Well, it still adheres to the dynamics of the system, so you can couple how you want it to move and basic constraints, but eventually, like as you said, when you move your feet, your center mass is going to move. When you step forward, your center mass is going to move. But you can add decouple analysis of it.
Can I make a quick comment about that? Yeah, there's a technique called feedback linearization that can be used to decompose a complex nonlinear dynamic system into a set of linear ones. And that allows you to treat the center of mass and the tip edge separately from a control and flow through computation standpoint while guaranteeing that they're all consistent.
There we go. So this is work done by Professor Williams' group, which is actually pretty cool. There we go. So this is the robot doing the same kind of thing on Mars now. So it's walking on stones and planning its footsteps through a pretty complicated environment. Stones are not exactly in the path where you would normally want to walk, but you can move them around as long as you're within the flow tube. You'll get to wherever your goal state is. Here. How do you start this? Awesome. Cool. So that was how to compute flow tubes, and and another way that you can also compute flow tubes is by learning. So you can have some kind of example, move through trajectories from one state to the other, and you can estimate a flow tube based on where the trajectories are, as long as the flow tube encompasses all possible trajectories, which is possible.
Is the dynamics always linear? Because I thought like if you're polytope and if you like if you're complex polytope and you like use a nonlinear dynamics and you move a little bit, then you can not be in a complex shape, right?
Well, you can plan nonlinear systems too, but as far as I'm concerned, I'm not really sure. You have to Professor Williams.
The polytopes generally require linearization of the system, and there's a limit to the validity of the range of the linearization, and that's included in that's one of the things that limits the size of the polytopes.
But it is the case that, I mean, it's kind of the standard thing that you do for nonlinear systems, right? Which is you're making them piecewise linear, but you are linearizing them at every step. And there's other techniques that people have developed with flow tubes where you do require the input system to be linear. Right here it can be nonlinear, but it's an approximation.
Okay, so funnels, goal is basically to find a region that guarantees your safety under a bounded uncertainty. So there are regions of finite time variance throughout all time during that trajectory that you define. And so in practice, there's a trade-off between computation time and guarantees. So if your trajectory, if you compute more nodes, then you're going to be able to fill in these little gaps between each of the ellipsoids. Whereas if you lessen them, it's going to take less time to compute each ellipsoid, but it's also going to not be as guaranteed. And this is especially important when planning. So if you're planning in some kind of point cloud, then some of the points may be right here where one ellipsoid doesn't intersect with the other, and you might think that's a safe path, but actually it's not at all. Yeah, so an example is this little glider, which is given in the paper by Ani and Russ. And so what you start doing is you create your system, your function, and this is dependent on your state, time, and W, which is some kind of bounded uncertainty. And you choose the bounded uncertainty, which means that you choose some kind of reasonable estimate of how much can happen to your system that you didn't account for. So you start, your velocity can be different from what you want. Say your nominal velocity is 10 meters per second, you can have some kind of drag, or you can have some inconsistency in your motors, and so what you expect is that there's plus or minus 0.5 meters per second to your nominal. So when you start writing your equations, this is what you expect your robot to do, and then that can vary forward and backwards depending on what your actual velocity is. But then you add some kind of wind on your system, which some kind of cross-sectional wind in the x direction, which we see there. And so what that ends up doing is pushing your system away from where you want it to actually be. So now you have some kind of velocity uncertainty, and you also have a wind that can push you one way or the other. So how do you deal with that? Well, you start with your nominal trajectory that has the plane flying perfectly straight. Everything, there's no uncertainty, everything is deterministic, and it acts like you want it to. So right there, the wind hits it. So what do? You have to have some kind of control, some kind of controller to bring you back to your nominal trajectory and try to control you around the system. So a standard way to do that is to make to have a cost function and create your optimal trajectory. And this is this cost function basically it kind of mirrors an LQR controller. And by solving all these equations, which is a pretty standard process, and you find out how to do that, you get a controller that tries to bring you back to your nominal trajectory, and so you get back. You're happy. But you don't have any guarantees just with the controller. You don't have any guarantees on how far you can get pushed. You don't have any guarantees on where you're going to go and where your system can be pushed to. So when you compute the funnel, what you do is you choose a Lyapunov function, and I'll explain what that is in the next slide. And you try to minimize the space around that function and tries to bring it back. So what this is so you have some kind of your initial state, and I guess this would be the initial state, and the whole region, what you're trying to do is minimize it around it. So does that make sense why you do that? So your trajectory is basically going to go anywhere around here, and what you're trying to do is find the region of space that minimizes, that encompasses all of the places that your system is going to get to. So that's easy to do when you draw it out and you know exactly where your system's going to go. It's easy to just shrink your ball around it. But how do you actually compute that? So when you have that for each point in the trajectory, you know that you're going to stay within here because you're going to have some kind of, from your nominal trajectory, you're going to have different places where your system can go under the given conditions of velocity and wind uncertainty. You're going to go anywhere within that. But as long as you know you're still in that ellipsoid, then you're going to stay within those ellipsoids as you go down your path. Does everybody make sense? Okay, so the reason that you use Lyapunov functions is there's different ways to measure stability, and so there's different ways to measure stability in a nonlinear system. So in a linear system, you're either unstable or you're globally exponentially stable. So you're going to converge back to your to whatever stability equilibrium point you have at an exponential rate. But there's also in nonlinear systems, there's global exponential stability, there's asymptotic stability, and there's stability in the sense of Lyapunov, which is what we care about. So the difference between that is, so say this is your nominal, and globally exponentially stable means that no matter where you start, anywhere on the board, you're going to be converging back to this equilibrium point at an exponential rate. So that's the best case scenario, that's what you want. Asymptotic stability means that you're going to be going from somewhere on the board within a certain region back to this nominal trajectory, but it doesn't have to be an exponential rate. So you can do something like that as long as eventually you start converging back to it. And then there's stability in the sense of Lyapunov, which is, so say you're here, your system can be doing anything crazy as long as it stays within some certain thing, which in the 1D case we saw was the little ball going around it. So imagine there's like a ball for each of these, and this is where your trajectory can possibly go. As long as it stays within that, you can say your system's stable in the sense of Lyapunov. Does that make sense? Cool. All right. So knowing this, does that?
I just have a basic question. So the Lyapunov function is around a stable set point, but the trajectory has non-zero velocity. So what is the point that it's stabilizing around?
You can stabilize around a trajectory, which is also what the funnels do. So you have your little point here, and this is your nominal trajectory, some kind of state, and your wind can knock you this way, your velocity difference can knock you this way or this way, but as long as you're still within that, you're going to converge back to it. And this is so this is the value of your Lyapunov function, and these are the different states you can have. An important thing to notice is the derivative is negative definite, or negative semi-definite in this case. And that means that basically all your trajectories, no matter where you go, they're going to be going down this cone, and eventually they're going to go down to some value. So does that make sense? That's like pretty advanced nonlinear system stuff. But cool. All right. So once you know that, it makes sense to use the Lyapunov functions as candidates for computing funnels. So an ellipsoid is actually defined by a quadratic Lyapunov function, which down here, previously shown, the equation for an ellipsoid is sum v times s. So that was the equation for an ellipsoid that Gabriel showed previously. The quadratic Lyapunov function has the same structure, where you have this being x tilde, which is basically the error of your state. So it's some kind of x hat being the state that you're actually in, minus x0, which is the nominal point that you want to reach. So this defines the region around your nominal point, which would be somewhere in there, and the ellipsoid is computed by doing that minimization that I showed in one of the previous slides. And then you can figure out the region inside of it by solving that equation, and if it's less than 1, I believe you're inside. And those are all the red dots, which show that you're inside of it. So that's used when computing trajectories. You solve for, say that you're inside a point cloud, you know which points you're going to hit inside of this ellipsoid. So in your planning, you solve that equation for each of the ellipsoids, and you know if you're going to hit something or not. Alright, so this is a video that Ani did. And this is using the funnel libraries for collision avoidance. This is showing for just one funnel. The glider dynamics were shown in one of the previous slides. They were pretty simplified glider dynamics. But, so you see right there that there's objects and glider plans a path around them. So the funnels, this is one possible one. Right here, I'm pretty sure they tell it where objects are, even though they're not actually there, and it finds that funnel being one of the better ones. And you see that throughout the entire path, the glider will stay within the funnel. And then when you're searching with the online planning algorithm that was shown previously, it goes through all of these funnels and eventually finds the best safe one. You won't always find a safe one, as discussed. In this case you did, but it finds the best one by around the path. So one way that it finds the best one is by finding all of, so if you're planning a point cloud, you find all the points that lie within the ellipsoids, and the one with the least amount of points is probably going to be the safest one. So here's a bunch of different obstacles, and it safely maneuvers all of them. And there's some pretty dynamic movements, which is cool too. So within that, there's, well, let's see. Let me go back. Is there a way to like get back to like full screen here? Yeah, I can call. So with the online planning algorithm, here's one of the possible paths. You have your point cloud of trees, yes, and those were shown the previous, the little brown thing with the green, like foxy tree-looking things. Using a sensor model, you get the point cloud back, and as you're going, you plan your path. And the way that this works is every 5 meters you plan a path, and then as you're flying through it, you get new sensor information, and you can replan your path using the algorithm. So, let's see. And that'll guarantee that you're safe. And when you're flying, obviously you don't like see the funnels, but right here you can see there's probably one funnel here, and then another funnel that plans this way, another funnel that goes to here, and then another one that goes there, and that's a full path. And there's also a cool one because it shows that you go through the tree, and that's where one of the funnels is, rather than going around. Because possibly you start computing a new funnel, or you start searching a new library here, and you may not be able to make it out of the way in time, given what speed you're going at. Does anyone have any questions? Let's see. And this is the online planning algorithm that we saw before right now. And some of the references, the paper from the video that we just saw, that's given here, and that also goes through the example in more depth. Frizoli's was one of the original people that could do the flow tube. Hoffman Williams did the temporal planning for footsteps and decoupling the humanoid system, and I did most of the stuff on the quadcopter. I did some of that a couple years ago. So another important thing to note that was a big thing in my personal research was that even though you may not be able to compute, or that you may not find a funnel that necessarily finds a safe path, you can shift that funnel around. You can move it slightly up and down as long as the first ellipsoid is still within, as long as your initial state is still within the other ellipsoid. And that's easy to do because you can just give it a simple transformation between one state and the other, and if you transform this S matrix, then it'll transform your entire funnel and it'll shift it around. So you can find your best funnel, even though it may hit something. If it was slightly shifted to the left, you can just shift it using that transformation. So that's one of the funnels too.
Yeah.
So everyone understand funnels and flow tubes now?
So I have a quick question. So the size of the funnel is computed by the chance constraint there, right?
Yeah. If you want to give it some ridiculous wind, like 1,000 miles per hour, then you're gonna get huge funnels, but that's under some kind of reasonable, in this region of the forest or something, there's only 3 mile per hour winds or something like that. Yeah, that's based a lot on what your bounds are.
So do you have any algorithm in your mind that is like not using offline planning? So this mostly you do the offline and then you do online search. But if you're like in a wild environment, you know nothing, then do you have anything in your mind that is?
There are algorithms just a basic controller will try to get you back to normal trajectory, but there's nothing that I know of at least that'll guarantee you safety and it'll give you an all-encompassing region like a flow tube or a funnel. Because so flow tubes, you find there's an infinite number of paths that will get you from here to here with your system. Basically, like every little minute change that you have, and that obviously takes a while to compute and approximate. And the funnel also takes a while to compute with regions where it can go. So I don't know anything that'll online compute this region, but online you'll be able to compute some trajectory, and then your controller will take your state error and try to control it, but it won't guarantee anything.
With the funnels, how do you compute your initial set of states or the allowed initial set of states? You have these uncertainties like for the wind and velocity, but what about, the initial state is sort of before those disturbances happen, but you probably want more than one initial state.
Okay.
There's some eraser here.
Oh, yeah, that'd be good. Cool, thanks. So with the funnels, so you have your nominal trajectory again, and then your ellipsoids around it. So when your system starts, you have your initial state, and your initial state is going to be here at time t0. But over the time computed, you can go over here, or anywhere over here really, depending on what happens.
I just mean that you want to apply the funnel multiple times, and your initial state may not be exactly the same. So it should be possible to use the same funnel, even though the initial state is off by a little bit.
Yeah. Okay. So say that you chose this funnel first, and eventually, what actually happens is you do this, and you get pushed around, and then you end up here instead of this nominal one. As long as your next funnel that you plan, so you can start a new funnel at any point in this trajectory, as long as the next funnel is also, as long as you have the intersection between the point and the next funnel, and if you're within this region, and you plan the next funnel, well, what you do is you plan the next funnel with this being original x0. So as long as that's your next x0, and then this will take you on a new nominal trajectory.
Yeah, I'm just saying, asking how do you, for the one all the way on the left, that one, how do you define how big that initial region is?
Okay. So that one, say, if you start, say, not moving or something, and you get pushed, is that what you're asking for?
Well, I understand that you're using the uncertainty in V and W that essentially defines how big those funnels are. Do they also define how big the first one is?
Yeah, they do.
Okay.
So what you're doing, because what you want to do is use the funnels and have some funnel library and be able to use those throughout all time. And so you don't want, so I guess what if you're asking, the first funnel, you're going to start at some initial state 0 with no velocity, stuff like that. And so you're not going to have any uncertainty on the first thing because you know where you start in the initial state.
Yeah, I'm just asking, you know, independent of the wind and stuff like that, you might just be starting at a point other than what that nominal point is. So you may want to define that initial funnel size by some other criteria besides wind, because they're...
Okay. All right, so like your sense or like how sure you are about your initial location.
Yeah, and I mean, there's sensor uncertainty, but you know, you just may happen to be in, you know, if you're doing the glider experiment 10 times, you know, you may not start it from exactly the same position every time.
Yeah. Well, you should your funnel every time you plan a new funnel, you start at the nominal trajectory of that new funnel. So you're not gonna have this funnel, and you're never gonna start over here on the first one. You're always gonna start at this point.
Well, but if you, I thought the point of the funnel was so that you can reuse it without having to replan.
Mm-hmm. Yeah, you can move the funnels around.
Oh, you can move. Okay.
Yeah. That was So yeah, so every time you start a new funnel, you start at this nominal trajectory, but the next time you use the same funnel, you could be over here and you just shift the funnel down to exactly the same point.
All right.
So the initial state is never going to be anywhere starting at T0. It's not going to be somewhere other than the nominal trajectory, but at T1 it could be over here. And so you just shift the whole funnel around. And as long as your T0 starts at the new funnel, and as long as T0 is within the funnel of T last funnel, then you just shift it around. You can also like turn it as long as you can multiply this as.
It seems like the shifting and turning is a pretty complex search problem in itself. Like, is that a hard problem?
No, that was actually the. Did I get rid of this slide? I might have got rid of that slide. I shouldn't have, because that was the work that I did for the person. Let's see if I can get it. But yeah, there's a bunch of different ways to do it. I did a pretty not very smart search where I just looked for the funnels, the safest funnel being the one with the least number of points in the point cloud within that entire funnel. And then, let's see. Oh man, I did get rid of this. Let's see. But basically what I did was find the safest funnel, and if there still was a collision within the safest funnel, then I made a minimization problem as you shift it back and forth. And there was a cost function that, let's see if I can bring it up.
So you're doing an optimization of the online running of the...
Yeah. That was implemented in real-time simulation, but that wasn't implemented on the actual glider as of 2 summers ago. So, let's see. I'll write it on the board. And you also I also made it so you minimize the amount that you shift it to. So you don't want to shift it completely somewhere else because it won't be near your path, and you'll end up doing some dynamic behaviors. Like you'll be flying, and then if you compute a funnel that's here that's kind of safe, but you shift it all the way down to here, your glider's going to be doing something crazy. That may, well, I guess it would be guaranteed to be safe, but I minimize it for at least the amount of shifting. Does anybody have any questions? So. Yeah, so does anybody have any questions on?
Can I ask one? So you've given us models of bounded uncertainty in your dynamics. So if you use probabilistic models, then your funnels start looking like risk allocations. Is there an interpretation of one in terms of the other?
I know of, no, but I'm sure if you look enough, yeah. I'm sure somebody's been working on that. I'm not really sure that because I haven't done that. Yeah.
Talk a little bit about the interaction between the flow
tube selection or the funnel selection and the underlying path planner. So you have something that's planning the reference trajectory, right? That's separate from your flow tube selection or your funnel selection, and then you have to select the funnels or flow tubes that allow you to follow that trajectory the best you can. But what if, or how do they interact? Like, say, if you have a flow tube or don't have a safe flow tube or funnel to fit the reference trajectory.
Okay, so you're asking basically the difference between planning with like a funnel library and a trajectory library?
Yeah, kind of, sort. Well, because like I know like the checkout planner that uses like an incremental path planner, right? To plan a path or something like that, and then you fit. Are you fitting flow tubes to the reference trajectory?
You do that offline, so you compute. They're called like funnel libraries, or usually they're trajectory libraries. So even computing a trajectory in real time for a fast-moving dynamic system is going to be expensive, and then computing a funnel on top of that is going to be even more expensive. So what a lot of people do is they compute the library offline for a trajectory and plan using that. But on this one, you compute your trajectory, compute the funnel around that trajectory offline, and then you search through the funnel library. You don't search through trajectories and then try to fit a funnel around that one. You just search through the funnel directly.
If you don't have a very good library, then you might not get a very good trajectory. So.
Okay. Also, a cool thing about funnels versus trajectories is a lot of trajectories will be discretized for like speed. So you have your nodes, and so say this is what your trajectory does, and you have node points here, and you're trying to fly past a wall or something. If your wall goes here, your algorithm is going to search these points, and it's going to say, okay, well, this is a safe path because none of the node points intersect with this wall, so to fly, and you're going to go the little animation shenanigans. But a funnel, since you have this region around it, I did a bad job of drawing that, but okay. When you search the algorithm and see if it's less than or greater than 1, you're going to find all these points being in that region. So it also, although I guess that depends on how well you want to discretize it. If your trajectory is a bunch of really, really small points, then you're not going to run into that issue.
It seems like you could, like when you're building a normal RRT without funnels, truncate points, if you say, yeah, they're illegal, it seems that if you're automatically adding on to that funnel instead of generating an entire trajectory and then making a funnel, you could save computational time, precisely things like that. Do you know if that's done? Or?
No, I don't. I do know that, you obviously want to minimize computation time, but it's not a critical thing when computing, I guess, funnels and flow tubes, because you do that all offline. So, and you want to, I don't think it's even close to the point where you can online compute a funnel. It takes like 6 hours to compute a funnel. So, depending on how many dimensions your state has. So, yeah, it's not like you're flying and you compute one of these things. You'll crash like hours before.
Okay.